Okay, let's get started. I guess everything is working now. Okay, cool. So last time we started to talk about the so-called implicit regularization effect of the optimizers, and last time we discussed the very basic one, which is that if you use initialization 0, and then you use gradient descent, and you have a regression problem, a linear regression problem, then what you get is that you get a minimum norm solution. This is last time. And today we're going to talk about a case where we have nonlinear models, and we'll see similar phenomena, but we're going to have a somewhat different proof. Right. Okay, so I guess let's dive into the detail. So this is a nonlinear model that we, you'll see that this model is nonlinear, but it's not actually that much different from linear model. As you will see, there's a paper that can do a little bit more than this, but generally we don't know how to deal with very complex models like deep networks. So so this is the nonlinear model we're going to consider. So suppose you have beta is the parameter and x is the input, and the model is fx is equals to the inner product between beta times O dot beta and x. So O dot is the hard mod product, meaning the entry-wise product. So basically you entry-wise square the parameter, and then you take the inner product with x. So this is still linear in x, but it's not linear in beta. So in terms of like, and still the loss function will be non-convex because it's nonlinear in beta, and you do the loss function, you take the square, then it becomes non-convex. So it's not that interesting in terms of the model itself, because anyway you are doing a linear model. But from the algorithm, the implicit regularization effect perspective, it's still interesting because you have a non-convex objective function. And we're going to make this even more interesting by consider a special case where suppose you have ground truth is that y is equals to beta star O dot beta star times x, where beta star is R sparse. So the reason why we want beta star to be R sparse is that R sparse means that the zero norm of beta is less than R. Like you only have R non-zero entries. And the reason why we want to have this restriction on beta star is because we want to consider over-parameterized models. If you have over-parameterized models, meaning, so we consider the case where n is smaller than d. When n is smaller than d, if beta is fully general, beta star is fully general, then there's no way you can hope to learn anything from less than dimensionality number of data points. So basically, we make sure beta star is sparse, and so we're going to assume that n is smaller than d, but n is larger than some poly r. That's the setting where we are going to work with. And more specifically, and for simplicity, or without loss of generality, let's assume also beta star is larger than 0 entry-wise, because you can see that the sign of beta star doesn't really matter in terms of the functionality, in terms of the ground truth model. And actually, for simplicity, of this lecture, let's also assume that beta is just some indicator on some subset of coordinates, where S is a subset of coordinates and the size of S is equals to R. This is only for simplicity of this lecture. Okay, and now let's define the data. So I guess we have talked about that we're going to have over-parameterized model. So we have n data point and n is less than d. So this n data point are denoted by x1 up to xn. Let's say RID from Gaussian of dimension d of spherical covariance, and yi is generated from this model without any error. So the yi is just inner product of beta star times beta star. So, like is this the inner product of square of beta star times xi. So, and n is much less than d, but we assume that n is bigger than omega tilde of r squared. So n is roughly bigger than r squared. And this, so this amount of data points in principle is allows us to recover beta star. Actually, you only need omega of r to recover beta star if you count the dimensionality, right? So there are degree of freedom approximately. So you only need n to be larger than omega of r. But for the theory to work, we have to allow it to be larger than r squared. But still, you know, if r is very small, then you still can make n much smaller than d and still bigger than r squared. Let's say r is a constant. That's probably the right way to think about it. Any polynomial dependency on r is fine, and so that n is just something like a big constant, but n could be much less than d. Okay, so and maybe so far after we define this, you may wonder why we have to use this nonlinear model, right? The answer is no, you don't have to use it if you really want to solve the problem. So the nonlinear model is only introduced to study this effect, right? Suppose you really care about solving the question, then you can use the classical solution, which is called Lasalle. So, or in the more kind of like terms, using terms that we used in this lecture, you can use L1 regularization. So basically, so to leverage sparsity, I think, I'm not sure whether you all have this background, but typically people use L1 to, in some sense, encourage sparse vectors. I'm not going to get into detail there, but you can show that, if you minimize the L1 norm of theta of the model, then you can reconstruct sparse vectors. So in particular, I think suppose you have this model f theta x, which is say linear in x, then this is so-called Lasalle. This is L1 regress objective, which is something like this, plus lambda times L1 norm of theta. So and the classical machine learning theory, I'm not going to go into detail here. In some sense, this is, if you don't know the background, probably just somewhat memorize it or kind of like treat this as a fact. So the classical theory says that if n is larger than r, say, I think you need to pay a logarithmic factor here. If n is larger than r, then this objective function recovers the ground truth, right? So objective above recovers the ground truth. Theta star, which is the, you can I guess you probably already see that theta corresponds to beta up to the squaring thing, so approximately. So basically, if you just really care about solving this question, you view this as a linear model. You don't have to care about the quadratic thing, and then use L1 regularization to recover sparse vector. There's a rich, theory, a lot of like existing kind of theory about this. I'm not going to details, but this is something, somewhat believable because you are using the sparsity of the vector. And also another thing to note is that because beta And theta, the relationship between beta and theta is that theta corresponds to beta O dot beta, right? The entry-wise square. So then the 1 norm of theta is equals to the 2 norm square of beta. The 1 norm of theta is the sum of entries of theta, which is equals to the sum of beta I squares, which is the 2 norm square of beta. So basically, if you do the quadratic one, you should regularize L2 norm, right? So basically, this objective one corresponds to L2 regularized objective. So if you really want to use the quadratic one, you should do the quadratic parameterization. You should do this f beta x I square plus L lambda 2 norm beta squared beta 2 norm square, right? This is the objective with respect to beta, right? So in the beta space, you should regularize L2 norm square. In the theta space, you should regularize L1, right? So this is the classical solution. And now we're talking about implicit regularization. I think our goal is essentially basically saying that if you use small initialization, this is without regularization, without explicit regularization, this is kind of like basically doing the same thing as, let's call this 2. So as long as you use small initialization with beta parameterization, you automatically get this L2 norm regularization for free to some extent. This is not exactly the exact way to phrase to state the theorem, but this is the rough, basically the main idea. So more concretely, we're interested in this objective L high beta. Let's formally define it. I think I normalized by 4 here just because it makes the gradient looks cleaner. So but it's just constant factor. So 1/4n times the square loss, the mean square error, right? No regularization, right? So this is our objective, and we're going to do the optimizer will be that you do GD on L height beta with small initialization. And more concretely, so the algorithm is for some very small alpha larger than 0. We initialize beta to be alpha times all1 vector. So you don't know the support of beta, of course, right? You each initialize all the entries by alpha. And then you take a gradient descent update every time. So you say that beta t plus 1 is equals to beta t minus eta times the gradient at beta t. Okay, so this is the objective we're going to study. And we'll claim that this objective, this is the optimizer we're going to study. We're going to claim that this optimizer actually actually finds the beta star, even though there's no explicit regularization. Any questions so far? So here is the theorem. So the theorem is that basically, the shorter version of the theorem is that when n is omega squared, we can converge to this algorithm converges to beta star. And but I think there's a little bit kind of like with small alpha. But there's a little bit of detail, so let me state the main theorem. So I guess suppose n is bigger than big O of r squared log square d. So alpha, let me see. Maybe let's write it this way, I think, just to avoid confusion. So let's see, be a sufficient large constant. Suppose n is bigger than c times r squared times log square d. I think the dependency on the logarithmic factor is suboptimal. The dependency on the r probably is also suboptimal. And at alpha to be less than some inverse poly n to the c, then when the time t is total number of the total number of steps is less than 1 over eta times square root d alpha and bigger than log d over alpha over eta. So for this range of time steps, we have you can recover beta O dot beta in L2 norm with error alpha times square root d. Okay, so how do we interpret this? So I guess there are a few remarks for interpretations. So the first thing is that I guess this is something probably I should have mentioned early. So L hat beta has many global mean. And why this is because of overparameterization. Because you have, like, if you count the degree of freedom, you have n data points and d parameters, right? So you have more degree of freedom than number of constraints. So you have many global minimum, right? So that's one of the reasons why you have implicit bias. If you only have one global minimum, there's no way you can have implicit bias. And second thing, how do we interpret all of these quantities in the bound? So the runtime lower bound depends only on the logarithmic of alpha. So this means that you can choose alpha to be anything inverse polynomial. So alpha can be inverse poly, right? You can choose basically the constant c to be to be a constant. So then the runtime wouldn't be affected too much. And the error depends on alpha. So basically, if you want very small error, inverse poly error, you can just take alpha to be inverse poly, and your runtime is not changed too much. And there's an upper bound on the runtime, which means that you need to do early stopping according to this bound. So if you really believe in this, you have to do early stopping, but the early stopping is pretty mild, right? But pretty mild because you can see that the upper bound actually depends on inverse alpha. So if you take something like alpha to be 1 over d to the power 10, then your upper bound is pretty relaxed. You can run for a long time, right? So, and actually in practice, we never observe that you have to, if you really do this synthetic example, really run experiments, you never have to early stop. And I don't believe that you have to early stop. This is more or less artifact of the proof. But this artifact is not too restricted anyways, because it depends on alpha in the inverse of the alpha. So you can take alpha to be small to make the bound very relaxed. So we didn't pay attention to remove that completely, even though we believe that's possible. Anyway, so basically the right way to use this is that you take alpha to be something super small, and then your error is very small, and your runtime lower bound is logarithmic in alpha. Okay, so there's one small thing is that alpha cannot be 0. So why you don't take alpha to be 0? The only reason why alpha cannot be 0 is because 0, beta is 0, is a saddle point. So the nabla L hat beta is at 0 is 0. This is partly come from the quadratic parametrization, right? So we'll compute the gradient. You'll see that because you have the quadratic parametrization, everything, the gradient always multiplied by beta itself. So if beta is 0, then you just have 0 gradient. So if the gradient is 0, and we are analyzing gradient descent, no noise, nothing, right? So no one is stochasticity. So if you start at 0, you will just stay there forever. So that's why you cannot use 0 as initialization. But anything close to 0 is fine. In some sense, this log 1 over alpha that you pay, this log 1 alpha is how much time you have to pay to leave the saddle point. So, and the leaving saddle point is actually very fast. That's, in some sense, you can kind of believe it, right? Because you have a saddle point. How do I draw it? Like something like this, right? So like leaving it is kind of like you have, it's optimizing a concave function, and you are going downhill, right? You basically accelerate so fast that eventually you leave it very quickly. So, okay, cool. So, right, and in some sense you can interpret this as, you know, gradient descent is prefers minimum norm solution in L2. So maybe preferring, sorry, I should like preferring global minimum closest to initialization, right? Because we have kind of claimed that, you know, so actually here, I think we have somewhat alluded to this, but just be formal in this case, you can prove the following. So you can prove that beta star is actually the arc mean of the norm with the constraint that you fit the data. Suppose you try to find the global minimum with the minimum L2 norm, right? So this is the constraint, right? So this means you have a global minimum if it satisfies everything, and you minimize the 2 norm, then this is actually equals to beta star. And the reason why this is true is kind of like similar to why the L1 norm works, right? Just because the minimum, the 2 norm of beta is the same as the 1 norm of theta. And this one, if you replace this by theta, then this is true. And this part is by the standard theory, which I didn't show. But you know that if you look at all the linear models that face the data, and you look at the sparsest one, it's going to be the theta. Actually, technically, I think this should be arc mean to the O.2 because, sorry, to the square root, because there's a translation. Like the objective is the same, but the arc mean has the translation. I'm not sure whether that makes sense, right? So so maybe let's say maybe the easiest way to write this is the following. So these two are exactly the same, just because you have a translation. If you look at the mean, right? And for the first objective, the arc mean is beta star, and then you can somehow see that the arc mean also transfers, you know, just by taking the square root. So, and this is also the case for linear regression, right? Recall that we also proved that if you start with gradient descent with 0, and you do linear regression, you get the minimum norm solution that fits the data. So it's very similar, at least on the surface, from the formulas, like you have almost the same guarantee. But I don't necessarily believe that this is always the case for all the case. Like I don't feel like you always find the minimum norm solution the solution that is closest to initialization that fits the data. I don't think this is always true. It's probably, I think there's still something special about these examples. Yeah, we cannot just extrapolate generically. Okay, so now we are going to try to prove this. Any questions so far? The proof of this theorem is pretty complicated. I'll try to finish it in one lecture, but if we cannot, I think I'm going to refer you to the notes. The notes has a pretty detailed derivation. So, to kind of get some preparation, let's try to understand some basic stuff about this loss function. So first of all, let's look at the population risk. This is the population no hat. So the population risk is y minus beta O dot beta times x square, right? So, and you can try to get rid of the expectation because this is population. So what you do is you plug in a definition of y, so you get beta star O dot beta star minus beta O dot beta times x square. And then this gives you, I think I have a 1/4 here. That's my population, right? Because I know I have the additional 4 everywhere. So, and this becomes 1/4 times the norm, the difference in norm. This is just because the expectation of some vector times x square, if x is Gaussian, this is equals to the norm of v, to norm square. So, and I'm going to claim the following. So you're going to have uniform convergence for sparse beta. So, but we don't have uniform convergence over the entire space, right? Because we have overparameterization. There's the, if you have uniform convergence for everything, then they wouldn't have any implicit regularization effect, right? So that would be the kind of the classical theory that we discussed in the first part of the the course, right? So, but we claim that if you look at sparse beta, then you have uniform convergence. So here is the I'm going to build towards this. So first, there's a claim which is with high probability over the choice of data. So for if n is bigger than something like O tilde of R over delta square, then for every V such that with, so support of V is less than R, or I guess alternatively you can write the zero norm of V is less than R. Then you have the following. So the empirical average of this kind of things, right? So why we care about this, I guess this is probably can be seen here, right? So this is the population has this form, something like V dot X square, and you take expectation. And this is the empirical one. I'm going to be more explicit in a moment, but this lemma is kind of like a small tool. So you're saying that if you have this empirical version of this V dot X square, and it's going to be very close to the population version. The population is just the 2 norm of V squared, right? So it's going to be very close to the population. But only for V, that is sparse. So this concentration only works. So if you have enough n's, right? If n is infinite, then you, or close to infinite, then you should expect this to work for every v, just because this is law of large number, or like a concentration inequalities, right? But here the concentration inequality is more subtle, or more kind of like there's a finesse here, because you only care about v's that are sparse, and also you only have this many of examples. You don't have a lot of examples. N is not bigger than d even, right? N is only bigger than the sparsity of v. So this is and actually this is also called, so, and also just for the language, I guess this is something useful to know. We don't really highly depend on this kind of properties, but we say that if a vector satisfies this condition, suppose let's call it 3. So suppose xi is satisfy 3, then we call, then we say this satisfy the RIP condition. So basically 3 is called R delta RIP condition. The acronym is a little bit kind of weird, but I think it's standing for restricted isometric condition. The reason why it's called restricted is because you are only restricting to vectors v, right? If you're not restricting to vector v, then this is a kind of like isometric condition, because you are basically saying that all the xi's are isometric, right? They are kind of spreading the entire all the directions equally, right? The xi's has covariance identity. That's pretty much what you are saying, right? So if you require this for every v, then you are saying that the covariance of, so what this is really saying, this equation 3 is really just equivalent to sum of xi transpose times v transpose times v is right, this is like bounded by v transpose I times v times 1 delta larger than 1 minus delta times v transpose I times v, right? So if you require this for every v, so suppose require for every v, then what this is saying is that the sum of xi transpose small n is, in PSD sense, how do I write this? What's the, wait, how do I write in PS? Wait. Oh, okay, right. Blank annotation for PS, yeah, like this. Less than 1 plus delta times identity, and larger than 1 minus delta times identity. So if you require it for every v, you are basically saying the covariance of xi are I think it's not called isometric, it's called isometric, isoparametric. It's just covariance is close identity, right? That's, I'm blanking on the word. So basically you are saying the covariance is close identity, but you are not requiring it for every v, right? And also this is not true for if you don't have enough data, right? So we only have n is less than d data points. So in our case, this matrix is not even full rank. How come you can expect a full? This only has rank r, because it only has rank n, because we only have n data points. N is less than d, so it's not even a full rank matrix. How come this can be close to identity? There's no way, right? But if you look at the quadratic form, right? So if you look at the quadratic form, and you only look at the quadratic form evaluated on sparse vector v, then this matrix becomes effectively look like identity. That's basically what this condition is saying. Right. Okay. So and once you have this lemma or this claim, then we know that you have the uniform convergence. For beta, sparse, for sparse beta. And this is just because, L hat beta is this 1 times 4 times 1 over n times sum of beta O dot beta minus beta star O dot beta star times xi squared. And this is of this form, right? So you can treat this as V, and then you're in this form, like V dot xi squared, right? And this V is sparse if beta is sparse and beta stars are sparse. Beta star is always sparse. That's our assumption. And if beta is sparse, then this thing is also sparse. You pay 2R sparse, right? They were R sparse, and now this whole thing would be probably 2R sparse at most. So then this means that this is close to the norm, right? So 1 times 4 times the norm of this. And this is equals to L beta, right? So for sparse beta, you have the uniform convergence, but you don't have uniform convergence over the entire space. So in some sense, so and also you can have uniform convergence for the gradient of this if you really care about it. I think I will show this later for sparse beta. So you can even show that the gradient concentrate around the expected gradient, the empirical gradient concentrate around the population gradient for sparse beta. So however, on the other hand, there exists dense beta such that, for example, L hat beta is 0, but L beta is very much larger than 0. So there are overfitting positions. There are places where you don't have the property that training and test laws are similar. But those are dense beta. Okay, so the question is why you are finding a sparse one but not a dense one, right? Because the dense one doesn't have the nice property. So the main intuition is the following. So we have done quite some preparation. So the main intuition or what we believe to be happening is that following. So you can think of this, maybe define XR to be the set of vectors that are sparse. So beta such that beta are sparse. Let's see whether I use the. So suppose you look at the space, right? So you have an entire space which is probably something very large, and 0 is somewhere here. This is the origin, and you have some family of, let's call this XR. This is the family of sparse vectors, and you know in this XR everything behaves so nicely. The training and test are just basically the same up to up to some small error, right? So the training and test, and also in terms of the gradient, they are similar. The gradient of L hat and gradient of L are similar. And I think basically what happens is that you start from somewhere close to 0, and the reason you cannot start at 0 is just because the saddle point, not very important. And you can think of like a gradient descent. So you are doing gradient descent on the empirical laws, L hat beta. And because you have uniform convergence, you are basically doing the same thing as gradient descent on L beta, as long as you don't leave this set XR. Right? So if you leave it, there's all bets are off, but if you don't leave it, it's fine. Right? So it turns out that what happens is that if you do gradient descent, you can consider the alternative world where you do gradient descent on a population. So let's say this is the gradient descent on a population loss L beta. And if it turns out if you do gradient descent on a population, you're going to reach a point which is beta star, which is kind of on the boundary of this set. And also in this trajectory, you never leave this set XR. Right? So now, because you believe that the black trajectory is similar to the purple trajectory, as long as they are in the set XR, and the purple trajectory is never leave the set XR. So that's why the black trajectory also converges to beta star. I'm not sure whether that makes sense. So basically, the purple one is the population trajectory, and the black one is the empirical trajectory. So you know that the empirical trajectory and the population trajectory are similar in the set XR. You don't know anything about outside the world, right? So, and also you know the purple trajectory never leaves the set XR. Then the black one probably shouldn't leave as well, and the black one should be similar to the purple one, right? So for example, suppose the purple trajectory look like this. Suppose that's what's happening. Then you lose control because at the beginning you are following the purple trajectory, and then you leave this set, and then all bets off. You don't have any control anymore. But this turns out to be not what's happening. What's happening is that the purple one actually stays in the set XR, like for a long time, like until it reaches beta star, and then stay at beta star. So that's why this alternative situation doesn't happen. This doesn't happen. This is not what's happening. And inside this XR, everything behaves nicely. There's only a global minimum, which is beta star. There's nothing else. And outside XR, there are a bunch of different things, right? So outside XR, you can imagine that there is it's a different color. So outside XR, there's probably quite a bunch of overfitting solutions. So these are all solutions that makes the empirical loss 0. There are so many of these solutions. But you never get to actually even go to those places just because your black trajectory is imitating the purple one, and the purple one didn't go to those places, and the black one doesn't go to those places either, right? So that's the intuition why this is working. Any questions?
Mind briefly, like justifying why the gradient descent on alpha beta doesn't leave the.
Well, why the purple one doesn't leave the? Yeah, so that's not. I didn't give a justification either, right? That's something we're gonna prove. Yeah. And I don't think this is something about the property of this problem. If you see the proof, it's not that surprising because you are in some sense, in a sense, trying to, it's a local search algorithm, right? So you are trying to search your neighborhood first, right? So you're gradually kind of like, you start from 0, somewhere close to 0. You are gradually searching your neighborhood until you find the global minimum. That's why you don't want to, probably wouldn't go this circuitous way, right? So like, so you're gonna go more straight to the closest point. But the real proof has to go through the math.
My other question is the initialization scheme we described before isn't in XR. It's like alpha times.
Yeah, that's a great question. So the initialization alpha times 1, right? So this is, literally speaking, is not in XR, right? It's that. And I got asked this question many times, and I think the right way to think about this, I think I had some remarks somewhere else, but you asked it early. I probably should just really answer it here. So the question is why the initialization is not in XR. But I think the thing to think about is that, of course, it's not exactly in this sparse set, but it's close. And close in what sense? Close in the sense that alpha 1 is very close to 0, and 0 is in this set. So that's the kind of like the property we're going to use. So yes, so you are right that we can never say exactly in a set XR. You're going to say that you're in the neighborhood of XR with a little bit small error, and the error is very small. It depends on alpha. So and if that's why we have to choose alpha to be very small. So in some sense, you really want to choose 0. So like from all of this discussion, the only thing you want to do is to choose 0. But 0 it just happens to be a saddle point. That's unfortunate. So you have to perturb it a little bit. Yeah. So the question is whether this particular property has anything to do with the positivity of beta, right? So I don't think so. Because, so are you talking about the positivity of beta star or beta, the variable beta? Beta star, right? So we assume the beta star to be positive. I think no matter beta star or beta is positive. Sorry, no matter whether beta star is positive, beta star square is always positive, right? So you can, if you initialize from this, then you just always go to the positive. It's always keep being positive. So basically, you just learn the absolute value of beta star. And if learning the absolute value of beta star is not that different from learning beta star. So basically, suppose you don't restrict beta star to be positive, then you cannot claim that you recover beta star. You can only say you recover the absolute value of beta star. Yeah. But the picture, the intuition is still the same after that changes. Mm-hmm. Yeah. Yeah. So the question. Yeah. So I guess the question is whether you really have to be exactly alpha times R1 vector, right? So and the answer is, this is a great question. The answer is no, you don't have to do that. The only thing you have to do is that initialization beta 0. This is a vector. I think you only need to make sure every entry of it is very small. So you only need to make sure this infinity norm is very small, less than something like alpha. And yeah, and you can even initialize negatively, I think. So if you initialize negatively, then the action will become negative eventually. But the sign doesn't matter that much, so that's fine. Yeah, but yeah, so and I'm only doing this just for convenience because it makes the proof cleaner, right? Okay, so given this plan, this intuition, so it's natural that we should start analyzing the population trajectory, right? Like the purple one, right? So and then we try to say that the black one is close to the purple one. So let's start with the population trajectory. Right, so you can in some sense think of this as a warm up, or in some sense this is also a kind of sanity check for this approach, right? So this is a, let me state the theorem formally, but I think you expect what the theorem is saying, right? GD on the population loss will converge to beta star, and in I think of log 1 over epsilon alpha over eta iteration with epsilon error in L2 distance. Okay, so but I guess the formal theorem matters less than the proof. Let's see how the proof goes. The proof is kind of brute force because you just really literally control what each of the coordinates is doing. So it's pretty explicit, and you see how the coordinates are changing. But the explicitness is actually a weakness in some sense because you are doing so explicit derivation. It's great for this problem, but it's harder to be extendable. I think that's a general thing, right? So if you have a very kind of strong analysis for toy case, that's not necessarily always the good case, because if it's too strong, too explicit, then the extendability, the applicability to broader case becomes a problem. And this is, in my opinion, probably the main reason why we cannot extend to more general cases other than this simple quadratic one. There's a small there's extension to the matrices case, but not fundamental extension. So you can change all of these to matrices instead of vectors. That's still fine, but not beyond that. Okay. So, but still, anyway, let me do the analysis. So the proof sketch is that you first compute the gradient. We call that L beta So L beta is equals to 1/4 times beta O dot beta minus beta star O dot beta star 2 norm square, and you can compute the gradient with respect to beta. It becomes beta O dot beta minus beta star O dot beta star times O dot beta. I guess you can kind of verify this, with pretty much, scalars, but vector version is pretty much taking the sum of the scalar, all the dimensions, right? So here, all the dimensions are separated. So basically, this is just the sum of the objective, and each objective is about one coordinate. And this is just a simple chain rule. And you can see that everything is multiplied by beta always, right? The gradient is always multiplied with beta, and this is why gradient L0 is 0. So, and now let's look at the update. The update will be beta t plus 1 is equals to beta t minus eta times this beta t O dot beta t minus beta star O dot beta star times O dot beta t. Okay, so and this is everything is in d dimension, but really you can view this as d separate update. In d coordinates, because each coordinates are not having any kind of correlation with anything else. So this is really just saying that bti is equals to bti minus eta bti square minus b star I square times bti. Okay. So every coordinate are just doing separate things, and maybe it's used, but this different coordinates has a little bit differences, right? Because this one is different. Otherwise, all the coordinates are doing the same thing. So the target is different. So in some sense, you are basically, so when I is in the support of beta star, which is denoted to be S, so then your update is basically beta I is updated to be beta I minus eta beta I square minus 1 beta I. And when, I guess I'm omitting a t just for notational simplicity, and if I is not in the support of beta star, then beta I is just updated to be beta I minus eta beta I squared cube. So, and you can see this all of this intuitively makes sense, because suppose this is the case, then so beta I is suppose is less than 1 between 0, right? Suppose that's the current beta I, and this number is negative, this is positive, so this whole thing is negative. So you are trying to increase beta I, right? So basically this update is trying to increase beta I if beta I is not yet reaching 1. And this update is doing the reverse direction, right? So this is trying to say that as long as your beta I is bigger than 0, then you are trying to decrease your beta I. So basically here, this encourages beta I to go to 1, and this encourages beta I to go to 0. And that makes sense, because 1 is the beta I star and 0 is the beta I star in the other case. Right, so okay, so and now let's try to do a more detailed calculation to see what happens in each of these cases. So let's first look at the case 1. Let's say this is case 1 and this is case 2. So case 1. So here we are trying to, the update is trying to increase beta I until it reaches 1, right? So there are still 2 separate cases. So the first case is that suppose beta I is less than, so at some time t is less than half. So you are only half done your work. And then you can see what's the changes. So beta I t plus 1 is equals to beta I t minus eta beta I t squared minus 1 beta I t. And we argue that this is trying to increase beta I, and we can see how much it increases beta I. it increases beta I by this factor, eta times 1 minus beta I t squared, right? So you have a multiplicative factor. So in some sense, you're multiplying your beta I to make it bigger. But how much you make it bigger, it depends on the value of beta I itself. But if we know that beta I is not too big, then we can bound this by beta I t times 1 plus eta 1 minus a quarter, which is bigger than beta, is equals to beta I t 1 plus 3/4 times eta. Right. So you have exponential growth. And if beta I is already bigger than a half, right? Then let's see what happens. So now the growth rate might be slowed down, because if you see, if beta I is kind of close to 1, then this constant becomes close to 0. So your growth rate slows down, and that's true. But what you can do is you can analyze how far you are away from 1, from your target. And if you look at how far you're away from 1, then you get the following recursion. Minus eta times 1 minus beta I t squared beta I t. And let's try to reorganize this a little bit. So I guess let's assume this. Let's assume this is also less than 1. And then this is less than sorry, let me think. I guess I don't necessarily have to assume this. Let's remove this for the moment. This is less than 1 minus beta I t minus eta t squared times a half, right? Because beta I t is bigger than a half. And now you can factorize this to get a factor 1 minus beta I t out. And this 1 minus eta 1 plus beta I t times a half. All right, and I guess it might be a little bit kind of like you may feel like this is a little bit unnatural, but I think if you see my final target, I guess it's probably actually not super difficult to guess how to do the intermediate steps. So now I'm going to use the fact that beta I t is bigger than 0. So I get 1 minus beta I t 1 minus eta times a half. So my point is that if you look at the final outcome, you see that now you are not growing exponentially, but you are converging to 1 exponentially fast. So you are decreasing your error. You are decreasing your distance to 1 in an exponentially fast rate. So in some sense, this behavior of this dynamics has 2 regimes, right? So when you are small, you are growing very, very fast. And then when it becomes bigger, then your growth rate slows down, but you are converging to 1 exponentially fast. So that's why if you combine these 2 regimes, then and also you can see that this maintains beta I is less than 1, right? So because if before you are less than 1 and later you're going to be also less than 1. So basically the behavior is that if you summarize it, so basically in log 1 over alpha over eta iteration, you are in the first regime. So this is beta IT grows to a half exponentially fast. Exponentially, right? And you only need to use this number of iterations because you initially is alpha and you want to grow to a half. So I guess technically you also have a 2 here if you want. Right, so and you have a learning rate eta. So basically this is because 1 over eta the half to the power, suppose this T1, this is something like at least, sorry, this is, I guess this is your growth, the factor that you growth, and you find some power to it, and then you want to grow at least a half over alpha factor, and that's how you solve this number T1. Okay, but anyway, so this is how, okay, the first part, and then in log 1 over epsilon over eta iteration, beta it converges to 1 minus epsilon. And this is because you want to start from a half, the error half, to error epsilon. And each time you decrease by 1 minus eta over 2, so that's why you have to pay this number of iterations. Does this make sense? I guess this there is a small thing that I probably skipped in some sense, right? So this is about how do you kind of derive how many iterations you need, right? So if you want 1 plus eta to the power t to be bigger than some number r, then this means t needs to be bigger than log r over eta. So this is just something that burning into my head. Like you can you can derive it yourself as well. Okay, cool. So all right. So that's what happens with those coordinates that you want to converge to 1. And you also have case 2. And you can do the same thing. I don't necessarily want to bore you with all the derivations, but I guess the derivations here is easy because you are just trying to say beta I is decreasing, right, in this speed, right? So, and here, let's see. And here, interestingly, so if you really literally look at this, this is actually saying that you are decreasing beta I eventually to 0. But somehow we care about something weaker that is more, let me see. Am I missing a plus here? So I don't know why I think I'm not missing a plus. Just one more. Let me make sure I don't make any mistake here. Okay, so I think what I do here, like I have some derivation here, some small claim here, which is particularly useful for the empirical case, which I'm not sure I can get into. So I'm going to skip this part. So at least for now, it's kind of trivial to see that beta I is decreasing. Right? If you start with alpha, then it keeps being smaller than alpha. That sounds trivial to see, and maybe let's just leave it there. This is enough for us to deal with the population case, right? So basically, our conclusion is, you can see that the conclusion is that you converge to something close to 1 in this number of iterations, right? And the iteration count is something logarithmic times 1 over eta, and you also have this property that you are always less than 1, right? All the entries are less than 1. And also, the small entries are never growing. So basically, your beta t at any time basically looks like there are a bunch of entries which is growing, right? So the S, and also in the S complement. In the S complement, all of these entries is less than alpha forever. And in this in the x coordinates, you are growing potentially. So you can see that this is still always approximately R sparse, because at least you only have R big non-zero entries, and all the other entries are very small. So approximately, this is still always approximately in the XR, just because the small entries are keep being small. Okay, so now let's try to talk about the empirical case a little bit. I think this full analysis probably wouldn't fit within 15 minutes, but I think I can give you some idea about it. And actually, I'm going to only do the case when R is 1, because when R is more than 1, it's kind of like a little bit complicated. So I'm going to do the R is 1 case. So get that. So for some delta, and when R is 1, and it's less than omega of 1, so basically you only have to have logarithm of examples, and then GD on beta hat. This is just a simplification of the theorem we have already stated. I guess now I guess this is also actually weaker. Maybe I should say it's a weaker theorem. Not only weaker in the sense of simplification, but also weaker. So weaker and simplified. So you get this iteration steps. We have it's less than O to the 1 over square root. So here, I guess this is why this is weaker than what we have said before. Before, the error can go to 0 as long as you take alpha to be small enough, right? So this is weaker because error doesn't go to 0. So before, we can make the error goes to 0 as alpha goes to 0. And now you only prove that it depends on something like the number of examples. This is just a technicality. Like if you want to prove the case when the error goes to 0, you have to do extra work, which is probably too much for this course. Right. So how do we do this? So in some sense, the proof is trying to, in some sense, maybe the proof idea. In some sense, it's pretty intuitive. Like given that this figure we have drawn. So you're just trying to show that L hat beta is close to L beta, and that's something you can prove very easily. So you try to prove that. So one, you try to prove that L hat beta is close to L beta for every beta that is, I guess technically you have to say this is approximately sparse, because you can never be exactly sparse as we discussed. So that's something that is relatively easy. And the second thing is that you want to say that the beta t for the empirical case, in the empirical trajectory, never leaves this XR very far, right? But never leave it significantly. So how do we show 2? Basically, you are trying to say that you are staying close to so you basically want the error to not blow up. So what does that mean? So it means that maybe let's draw something here. So you are trying to show two trajectories that are close to each other just forever, right? So you have a trajectory, which is the purple one. This is the gradient descent. And what happens is after you take the first step, you have some error here, right? So now these two trajectories are not doing the same thing anymore, right? Initially, you are taking the gradient at the same point. And now this purple one is taking gradient at this point. And the black one is taking gradient at this point. So you have this error in not in terms of the gradient are different, but also in terms of the difference of the points where you are evaluating your gradient. So it's empirical versus population, that's one difference. And the other thing is that you are evaluating the empirical and population gradient at different places. And that could introduce a bigger error. And then it will introduce even bigger error. So if you don't do this carefully, then it's possible that eventually you go this way and the other one goes the other way, just because the error keep being bigger and bigger. So basically, you have to kind of control how the error changes. So that's the key part. And this boils down to a lot of kind of like, at least on the surface, seemingly very boring calculations. If you really want to do all this calculation well, you have to understand a little bit about what each term means, and it does require some extra work. But the first level thing is that at least this whole thing is a simplification of one of the paper I wrote a few years back, and when we did this thing, like the first thing we tried is that we just try to do the calculation. So and you try to understand which term is problematic, which term may cause bigger flow up, and then you focus more on that term, and then try to understand a little better, and then maybe use some devise some inequalities. But basically below this level, like it becomes like quite technical. So so I think I'm going to probably spend another 5 minutes to do a little bit like things. So I think the thing for you to kind of control this error is that one thing we realized is useful is that actually this is actually important, kind of like conceptual, semi-conceptual kind of like thing that we realized, right? So to control how this error is good to represent your iterate in a convenient way. So what does that mean? So it means that beta star, we assume R is 1 already, right? So let's assume beta star is just E1, right? So it's just a 1, 0, 0, 0, right? So you just want to say that you converge to this vector. And one of the useful thing we did is that we take beta t to be, we write beta t to be RT times E1 plus an error vector zeta t. So explicitly you write it as a multiplication of beta star and some error. So in some sense, like beta star is here, and you're starting from 0, and you try to say how much you are different from this line. So this is your zeta t, and this is your RT times E1. That's how you represent where you're at time t. And you want to keep, and what we did is that we want to say the RT. The plan is that you want to say RT is going to 1, because eventually you want to go to E1, and zeta t, the error term, is always small. I think we prove it to be smaller than O of alpha for any t. That's the next level, right? So and then you basically, what you have to do, you have to try to derive a recursion for RT and zeta t, right? And when you derive the recursion for both of these two things, right, you can always keep in mind that what happens with the population, right? So the recursion for RT, and you can have the same recursion for the population case. So basically you're gonna have so suppose let's for example talk about, let me see which one I can talk about easily. Let's see. how do I quickly simplify this notes? I think I had some backup plan. Yes, here. So basically, for example, if you look at the recursion for RT, it looks like RT plus 1, RT is equals to RT minus eta RT squared minus 1 times RT minus some term that depends on zeta t. So if you do, like, I have all of these formulas written here, but I don't want to show all the details. So, and if you look at this, this is very similar to the thing that we had before. I guess I don't know why my bad. Let me also change the superscript. I think I should probably have, yeah, in my notes is also superscript. Okay, I guess let me now change everything. Just like the superscript is the same as the here. So if you look at this one, this part, this is the same as the update for the beta we had, right? So where is the update for beta? Here, right? So this is the case when you are looking at a coordinate where you have a entry 1 in the beta star. So, and this is the update, right? So, and if you just replace beta I to the RT, you get the same formula, right? So RT has the same formula. So basically this part is what the population gradient does. And you already analyzed this part already. So so basically the only thing you have to deal with is how does the error term affect you. And you inductively show the error is small. So under the assumption that error is small, then you can show that the update for RT is basically doing the same thing as the update for the beta t before. So that's how you deal with RT. But how do you know that zeta t is small? That becomes even more complicated because zeta t also has a derivative, has a recursion, right? So zeta t has a recursion, which is, I think I don't even see a simple way to write it. Actually, I have something like this. So zeta t is equals to zeta t minus something like some matrix mt times zeta t. Some vector, sorry. Some vector rho t times zeta t, something like this. I'm not going to define rho t. And what you do is that this is somewhat similar to the case to those I not in S, the beta I t recursion. So it's not so okay. What's the beta I t recursion? The beta I t recursion was something like beta I t plus 1 is equals to beta I t minus eta beta I t cube. So I think this, if you really look at the derivation, I think this is something like beta I t squared minus 0 times beta I t. So if you really do the match the terms, I think these two matches and these two matches, and something here which also matches if you look at the details to some extent, not exactly, but you somehow kind of have a there's no way to match everything exactly, but you just use the beta update as a reference for you, and you know that something already matches, and what doesn't match is this rho t, which I didn't define, to this beta t squared, and you do some kind of like concentration to show that they are similar. And what exactly concentration you show, it's also actually up to the exact terms. And somehow sometimes you relate the zeta t recursion to the beta t recursion under the hood, so that you can show that zeta t doesn't grow eventually, right? Because you knew beta t doesn't grow, right? That's what we proved easily. And once you can relate zeta t to beta t, then you can also try to show zeta t doesn't grow eventually. I think that's pretty much the best thing I can do in a short amount of time. And the details are in the notes. Any questions? Sorry, yeah. Yes. I think it was RT plus one when I changed the superscript to subscript. I forgot. Yeah. Thanks. Okay, so the question is that. I guess the question is that, at least in this lecture and last lecture, we showed two examples where gradient descent convert this to a solution that is closest to the initialization. But why empirically you still have to use the explicit regularization like wave decay? So I think I would like to argue that empirically the wave decay is actually not very strong. So it's not even clear whether the wave decay is really doing a regularization, because with the same wave decay, actually you can memorize the training data. Like you can even memorize training data with random labels. So suppose you permute your label arbitrarily, so that there's no pattern, it's just random label. You can still use the same wave decay and train a network with the same wave decay to find a zero error solution. So that seems to suggest that the wave decay is not really doing that much of a regularization effect, at least not as strong as the theoretical setting would say. Right? For example, in this case, suppose, or in this case or the previous case, right? Suppose you use wave decay, you really find the minimum norm solution. Then use a strong like a regularizer to say you want to find a solution with small norm. Then you cannot fit random labels anymore. So and also another kind of like tricky thing is that the wave decay in practice also has some other effect that kind of regulate, for example, how the batch normalization is working. And like if, for example, I think like if you have batch normalization, then the model becomes scale invariant. So like it becomes like if you multiply all the ways by 2, technically it don't change anything. But somehow you want to regularize that. You want to kind of like regulate that in some way, because in certain cases it changes the optimization. So basically, okay, I guess I don't have a very concrete. This is a good question. I don't have a very concrete answer, but I think the thing we believe is that wave decay is not actually doing a strong work in terms of the standard normalization of the norm, like regularization of the norm. And also we somehow suspect that the wave decay has some other effect to some extent. And also sometimes the wave decay is not even important, right? So if you remove the wave decay, you still get pretty good results in certain cases. So I guess that's the best we know for now. Yeah. Any other questions? Okay, sounds good. I guess I'll see you on Wednesday.